And today I want to present also on the topic of microplastic, but more the analysis side, also mostly waters is what we're currently focusing on. There's lots of different methodologies, and I just want to present today or give you a brief overview of the Laserdirect infrared imaging system as a method to analyze microplastics. So the instrument has been recently developed by Attenuated Technologies, and we're working closely with them together in order to advance that method for microplastics analysis. Initially, it was designed for the pharmaceutical sector, so for the application of to look at active ingredients in tablets. So for instance, here at the bottom, you could see an aspirin tablet to see what is the morphological, what are the morphological aspects, and is the active ingredient actually dispersed well in the tablet. But at some point they found out that this instrument can also be quite well used to analyze microplastics. And how is that working? So in the end, it's a black box. We insert our sample into, we have to put it into on a IR Reflectance side, but then the instrument does its magic. So the heart of the instrument is a quantum cascade laser. This is where we mount the sample. So the laser will produce light at different wavelengths, which are then shown onto the sample, in our case, the microplastics. They are then reflected back into, sort of down the laser stream, into a MCT, which is the detector. And in the end, we will receive a spectrum. So this is basically the simple physical properties behind it. Every substance there is has a unique fingerprint. So every substance has their own spectrum. And we can then compare those to a library and then determine the polymer. So knowing the polymer by itself doesn't really make it sort of a microplastics analysis. So this instrument is coupled with an imaging system. So the imaging system provides information on the number of particles found, as well as this does the sizing, and then the LDIR function will do the determination of the polymers. And also, as Jack mentioned, especially the smaller particles are what we are interested in, because they are more prone to bioaccumulate or actually access cells. So this instrument will be or is able to detect microplastic particles between 200 and 300 micrometers. Obviously, there's a whole debate on where's the cutoff to migrate into cells, but so the instrument has also the ATR function for particles that are larger than 300 microns. The different way of doing that is called ATR, or Attenuated Total Reflectance, where the IR wave or the IR light is not shown through the sample, but basically shown into a crystal, which is then lowered onto the sample, or the crystal is lowered onto the sample, and then the light is shown onto the sample through the crystal and reflected back into the crystal, and basically diverted back into the detector. And we can then determine a reflectance spectrum, which then also can be viewed or looked up in the library, and we can determine the polymer. So this instrument is also useful for larger particles. However, because the crystal needs to be lowered onto the particle, and we don't want to break the slide below or damage the particle, it's a very slow lowering of the crystal, and it takes a while to establish a good spectrum. So it roughly takes about 10 to 15 minutes per particle. So this is for a environmental testing lab, not something we want to be doing for hundreds of particles. We can do that on occasion, but not something we want to be doing on hundreds of particles. So this is the information the instrument provides. So it's basically the imaging system that shows where we can find what kind of particles. It also detects natural particles like natural polyamide, SDS, or polyamide generally. We get the size and the morphology, and through that we generate a report for our clients. So those would be the current 8 polymers that are sort of most abundant, and we've also validated our library against those. And then at the bottom, or as also part of the report we generate, would be the size distribution. So we basically collect them in different size buckets, up to sort of between 20 and 300 micrometers. The pros and cons of the instrument: it's got a fast analysis time if you compare it to the FTIR, which is more or less currently the state-of-the-art instrument in microplastics analysis, next to the pyrolysis method or the simple microscope. The analysis time at the moment is around 250 particles in an hour, but our samples have about 300 to 600 particles, so it takes about 2.5 hours per analysis. We can gather specific information per particle, very low detection limit, so if there's one particle, we will be seeing it. It's a good method for smaller microplastics, but not for the larger. Especially the high resolution camera can take pictures, and we can provide our clients with those. And we can also use that for sizing, which is really accurate. The cons, on the con side, are particles need to be transferred onto an IR reflective slide, which is a bit of a problem because that could lose, or in that process we do lose particles, and we've quantified that with our quality standards, but it is a loss. And there's also a thorough sample cleanup needed in order to reduce the amount of particles that are on the slide, but also microplastics that could be underneath, I don't know, sand particles or organic matter. It's a new instrument on the market. It's very new for microplastics, especially. Only one peer-reviewed article was published recently, and the software is still in development phase. So we're working very closely with Agilent to do improvements in order to make it feasible for routine analysis. Also, the IR is in a fingerprint region between 975 and 1800. And also it's possible for larger particles to use the ATR function, but that takes a bit longer. So what matrices can we analyze? We've started with potable water, as that seems to be the most simple way of doing it. And we've, I think, established a really good method to do that. We've now ventured into new matrices as environmental waters and biota. So we're looking into oysters and mussels for the time being. Biosolids and sediments is still on our list to do, but it took a fairly long time to get the potable water method running due to various different things. Especially one was to get blank water. That seemed to be a very difficult task, which I wouldn't have thought in the beginning. And we've got some international cooperations. One, we've participated in the SQUIRP and JRC lab intercomparison studies, and as part of Eurofins, we're part of a sort of global network doing microplastics analysis, where we're the only one using the LDIR, but we've got access to other methods as the pyrolysis and also the micro FTIR. Just as a summary, microplastics is a really challenging new field of analysis. There's currently lack of clarity around reporting requirements and nomenclature. Also, definitions of particle sizes and shapes there's no regulatory body saying this is what we need to look out for. There's a large size range that can't be covered by our instrumentation at the moment, but there is none except for the pyrolysis method. There's lack of standard methods and around sort of sampling and analysis. And also there's different analysis techniques which have different reporting units. But I think there's great efforts of research being done worldwide to tackle this new field of analysis. And we're very proud at Eurofins, in cooperation with Agilent, to contribute to this challenging field. In our opinion, the LDIR is a great new analysis technique that can be used routinely, especially in comparison with the FTIR, which takes longer for the analysis. And I'd like to thank you for your attention, and I'm there for any questions.
Thank you very much, Julia. Please join with me in with a round of applause for Julia. And also, people might not realise this, but you're actually in the lab at the moment, and behind you is the LDIR. And in my opinion, in microplastics, accuracy, reproducibility, and precision are some of the it's some of the hardest things to do with microplastics analysis, and the work you're doing is moving us in that right direction. Could you tell me about the blanks? Can you tell me, I don't know if you're allowed to tell us, but how hard it was to get a blank blanked?
It was fairly hard. So we tried the general lab DI water sources, and we kept finding polyamide in great abundances. Especially our water purification system seemed to be spitting out lots of different microplastics at huge abundances. Also, it was provided with a 0.22 micron filter at the end, post filter or polisher, they call it, and that kept spitting out more microplastics. We've now established we now use a RNA DNA filter, which works well. We've also gone to the supermarket and bought very expensive waters from Norway or Tasmania in glass bottles, and we couldn't get a blank water, so it seems like a bit of a problem.